Hello everyone, I Nikhil welcome you to Vigyan Bharat. We are back again with another interesting video. Today I'm going to discuss the problem of the day for today, and it is based from linear algebra. The topic which we're going to cover today is first is the diagonalizability, the concept of diagonalizability. The second is what we mean by a nilpotent matrix, and finally what is an idempotent matrix. And based on all three notions, we're going to give finally a problem of the day which you have to solve, and I'll try to define first these notions for a linear operator and finally an equivalent formulation for a matrix. Okay, so without any delay, let's get started to the lecture. First, I'm going to discuss what we mean by an operator when we'll say that an operator is diagonalizable. First of all, you need to understand what you mean by an operator. Suppose I have a map T which is defined from a vector space V to itself. And of course this T is linear, that is, it preserves vector addition and scalar multiplication. Then in such case we call such a T to be a linear operator. What I call this T to be a linear operator. Operator because it's defined from the same vector space to itself. That's the reason of the operator. Okay. Now when I say this T is diagonalizable, if T has this matrix, this operator T has a representation in terms of a diagonal matrix where the entries of each entries on the diagonals correspond to the eigenvectors. These are the eigenvalues. The entries on diagonals are the eigenvalues and which correspond to the eigenvectors of these operator, this linear operator. So let's try to understand this definition which I have just written, that let T be an element of L of V, be a linear operator. Now what this L of V means, that L of V is the collection of all linear maps defined from the vector space V to itself. That is, I am collecting T such that how these T are defined from V to V, the same way which I had defined earlier, and of course they are linear. This V are finite dimensional vector space which I assume. If I collect all those maps and give a name to that set, then this set is the collection of all those such maps. Of course it forms a vector space which you can verify easily. Okay, so this linear operator is said to be diagonalizable if this operator has a diagonal matrix. That is, there exists a diagonal matrix with respect to some basis vectors of V. That is, our vector space has some basis vectors, and those vectors are precisely what I said are the eigenvectors of this linear operator T. What do we mean an eigenvector? Let me first quickly discuss. Suppose let this small, I don't have much space, let V non-zero be an element of the vector space. Then I say this vector space V is an eigenvector of the linear operator if this holds. That is, if I apply my T to V, then it is nothing but a scalar multiple of V, where this lambda is coming from field F, that is lambda is a scalar. The image is a scalar multiple of the vector itself. So such vectors, such non-zero vectors are said to be the eigenvectors of this linear operator T, and these scalars lambda are called the corresponding eigenvalues that correspond to that eigenvector. I hope now it's clear. So if now this T, let's come back again to the notion of diagonalizability. When what I say, if this T, if I find its matrix representation with respect to some basis beta, where this beta consists of the basis vectors of the vector space, if I try to find the matrix representation of this linear operator, and if that matrix comes out to be a diagonal matrix, if it comes out to be some D where this D is diagonal, then in that case I say this my linear operator T is a diagonalizable operator. Okay, let's move ahead. We're going to understand what I mean by that again. Let's move ahead now. So this I have written, I think already, that this is an equivalent definition, but it says suppose my this T is a linear map from the vector space V to itself. Of course I assume that my vector space is finite dimensional, that is, it's less than infinity. Then T is said to be diagonalizable if there exists, this is important, if there exists an ordered basis beta for V. That is, you are having a basis basis for the vector space such that this is a diagonal matrix. Similarly, you can define the analog of diagonalizability for a matrix, because a matrix is nothing but a linear transformation. It's pretty simple. Let's discuss what I mean by that. If I suppose I have a matrix A of size n by n, then I can say this matrix A, I can view this matrix as a linear transformation from Rn to Rn, or you can say linear operator precisely, because both the vector spaces are same, Rn over R, and on the right I also have Rn, which is a vector space over R. So if I define how I define my linear operator in this case, this A acts on some vector from this space, that is our domain from where our vectors will come. So how it act? If I multiply this matrix on the left to this vector x, then the output, this belongs to Rn. See how this A is an n by n matrix. This x is coming from a domain which is of course Rn. So if you multiply A with x, let me rub this one. If you multiply A with x, that's very elementary. Then this resultant, this element is an element in Rn, because A has size n by n, x has size n by 1, so they coincide. So this is the size of the resulting vector n cross 1, that is simply n. So that's why this Ax belongs to Rn. So you can view this matrix as a linear operator from Rn to Rn. So that's what I have written. If a matrix A is said to be diagonalizable if the operator LA is diagonalizable, that is left multiplication. LA is this operator how I have defined, that is precisely this. Not that is also fine what I have written, but you better to write it this LA acts on X. This is how I define it here. This LA, the operator which was T in previous case for corresponding to the matrix, this has just a different convenient notation to write it, and it is defined like this. LA of X is AX, that is for every X in R. Finally, to make it more clear, I go again through one more last definition. You read it and you're going to get everything what you mean by diagonalizability if it's not clear in the previous two. Let's try to see it. Suppose let T be a map from V to V, of course linear, and I assume the dimension of my vector space over the field F is n, which is finite. That I mean that my vector space is finite dimensional. Then I say that this linear operator T is diagonalizable if and only if there exists an ordered basis beta. This ordered basis should have exactly n vectors because the dimension of the vector space is n. So this beta for V consisting of eigenvectors of T. So you collect all the eigenvectors from the linear operator in a set, then they set forms a basis because these eigenvectors will be linearly independent. You can just check it, and in that case we say that this operator is diagonalizable. Okay. Furthermore, if my operator is diagonalizable, if this holds, that is this above condition, I can able to find such a basis consisting of eigenvectors. Furthermore, if this T is diagonalizable and beta is an ordered basis of eigenvectors of T, then this my matrix representation, what is this? This is nothing but the matrix representation of my operator of T with respect to beta. Then if this matrix I give a name D, then this D is a diagonal matrix, and the elements of the diagonal are the eigenvalues corresponding to those eigenvectors which I have found earlier of the linear operator T. So that's all. I hope it makes sense. Now quickly let's try to understand one by one some equivalent conditions for diagonalizability. If you understand, like equivalent, by equivalent I mean like either they are all true or all false. So suppose V is finite dimensional and T is an element of L of V, that is a linear operator on a vector space V. Then suppose lambda 1, lambda 2 till lambda m denote the distinct eigenvalues of my linear operator. Then I say that my linear operator is diagonalizable if the following conditions hold, that is the following are equivalent. If I say my linear operator is diagonalizable, then it is also true that there is a basis that previously which I have defined, which I denote by beta. So that basis consisting of the eigenvectors, these vi's are eigenvectors, v1, v2, vn all are eigenvectors. Option, what the next equivalent condition is that there exist one dimensional, this is very important, there exist one dimensional subspaces u1, u2 till un of v, each invariant under T. By invariant, by I mean, suppose I choose some u, just for one particular case I'm saying, suppose u in capital U1 and I apply T2 over it, then the image also belongs to U1. That is, if you take the element from some subspace and apply the operator T on it, the output also belongs to that space. In such spaces, such subspaces are said to be invariant under the operation of T. Okay. Then if your operator is diagonalizable, then you can express your vector space in terms of the direct sum of these subspaces, these invariant subspaces. Okay, so here what I have just spoken, I assume you know what we mean by direct sum. Finally, this fourth condition says that you can express V as a direct sum of the eigenspaces corresponding to eigenvalues lambda is. Suppose you remember we have m eigenvalues, these lambda 1, lambda 2, lambda m. We don't know how many eigenvectors correspond to some particular eigenvalue. We don't know. There will be one, there will be more than one eigenvector. So suppose I choose my lambda 1, some particular fixed value of, just for sake of understanding, I'm saying that if I consider this set, collection of those v in my vector space such that T of v is lambda 1 of v, all those vectors, this is small v, just make a clarification, this is not vector space, this is element of the vector space. So I'm collecting all those vectors in my vector space which satisfy this condition, that is T of v equals to lambda 1 of v, and I close it inside a bracket. Then I give this collection a name, E lambda 1 comma T, that is all the eigenvectors of the linear operator T corresponding to the eigenvalue lambda 1. Okay, so you collect all those vectors, then they are precisely called eigenspaces. Eigenspaces corresponding to the eigenvalue lambda 1. In this case, it may be any lambda I, you can just change the expression of lambda I there. So you collect all the such eigenvectors which satisfy this condition, then it forms eigenspace. That is, it will satisfy those conditions again because it's space, so it preserves both addition and scalar multiplication, this T. When I'm saying preserves, it means the linearity, that is T of v1 plus v2 is same as T of v1 v2, T of v1 plus T of v2, and by addition, scalar multiplication, I mean T of alpha v, there alpha is some scalar, is same as alpha T of v. Alpha is an element of v. So this I mean by preserve. So this v can be expressed as the direct sum of these m eigenspaces corresponding to each eigenvalue. Okay, and finally the dimension of a vector space is same as the sum of the dimensions of these eigenspaces. Okay, here which I have explained, I have defined here also, you can just read it quickly for your sake of understanding. The eigenspace of T corresponding to the eigenvalue lambda is defined as collection of those vectors in the vector space which satisfy this condition, and this is an equivalent way to write this in terms of the null space of this operator T minus lambda I. Now I explain how I have written it, try to understand it. V coming from the vector space is that if I write it like this, try to see this, I can write it T of v minus lambda. V can be written as I of v. I is the identity operator. I of v is defined as v for every v in my vector space. So I just replace my small v by I of v. If I now, I can rewrite it like this, lambda I of v. Simply algebra, nothing more than that. So this might becomes an operator. I'm searching for all those vectors which satisfy this condition. That is an equivalent to say that all those vectors which belongs to the null space of this operator t minus lambda I. I is an operator, t is an operator, so their difference is also an operator. Because it will preserve, again, what I have said, all those conditions it will going to satisfy what we require for linear operator. Okay. So this is the equivalent way of writing it in terms of the null space of this operator. So now I have asked you a question. It's pretty straightforward, but you should answer me in the comment box whether all these eigenspaces will contain zero vector or not. It is pretty straightforward, pretty trivial. Try to answer me your justification. Why, if they are there, then why they should not? They should be present. And if they are not there, then why they should not? So if I repeat again, this is collection of all those vectors which satisfy this condition, to be very precise. Okay. So in such cases we say that a linear operator is diagonalizable if it satisfies all the previous definition. Then all these are equivalent. It satisfies these also. Okay. Now let's move ahead to nilpotent operator. Let's understand this. What do you mean by an operator to be nilpotent? By nilpotent operator, I mean that if I raise its power, that is, I compose the operator with itself, and I find a power after some certain steps, when I am composing my operator with itself, it becomes the zero operator itself. It equals to the zero operator. Zero operator is nothing but zero. It's a linear operator which maps everything to the zero vector of the V. That is, let me write it. This one. This is also an operator, so it is defined as 0 of small v is the zero element, and this is true for every v in the vector space. Okay. So such an operator is said to be nilpotent operator, and you have to find here the smallest such stage at which this occurs. Then in that case we say that such an operator is nilpotent with that index. Let me define what I have written. Just try to see what I mean by that. See, an operator is called nilpotent if some power of it equals to the zero operator. That I have asked you what is the zero here. Okay, it depends. Zero, like if this t is some function from some vector space to itself, then the composition will give you the zero function. If this t is a matrix from the vector space which acts on some vector space to itself, V can be, suppose A is n cross n matrix, then your V should be R into Rn, then this A to the power k becomes equal to 0, then that 0 becomes a zero matrix. So the context should be clear what this 0 is. Okay. Then I have written in terms of the matrix what you mean by a matrix to be nilpotent. A matrix n, of course, I assume that it should be square for in order it to be conformable for multiplication. A matrix n is called nilpotent if there exists an integer, positive integer or a natural number k, such that n to the power k equals to the zero matrix. Thus, the smallest k at which this occurs is called the index. Okay. And I have written this k is the least, that means the same. Okay. And there's an observation. If A is an n by n matrix, n is an n by n matrix, then your index would be less than equal to n. You have to answer me what's the reason for this. Why it will be less than. Try to justify me in the comment box. And this is the observation which I have told you. Not the observation, but definition to be very precise, that in such case the k is called the index of n, or n is said to be a nilpotent matrix of index k. And there is an observation, like if you raise the power of n after that stage, suppose your k is 2, that is n square equals to 0, then after all the successive powers will equal to be 0, n cube will be 0, and 4 will be 0. Why? Because n cube is nothing, n square times n. But you know that this n square is 0, so all these products, successive products, will become 0 like this. We can use the associativity there. Okay. Finally, idempotent operator or idempotent matrix. A square matrix is called idempotent if and only if you square it and get the matrix itself. Clear? if you square it and get the original matrix itself, then those matrix A which satisfy this condition are said to be idempotent. Note that A has to be square again. You have to answer me why. I have already answered you while explaining the last concept. Okay, so these were the three notions for today, and now we move ahead to the problem of the day, which is a very important problem. What it says, let's quickly understand this. Suppose let A be a 3 by 3 matrix. How it is defined: 4 minus 3 in the first row, 3 minus 2 minus 3 minus 1 1 and 2 likewise. Then you have to answer whether this A is diagonalizable, this A is nilpotent, this A is idempotent, or it's none of the above, or if there are more than one options are correct. So try to answer me in the comment box, solve it, go again through each and every concept which I have defined above. If you find like doubts in anywhere, feel free to drop me your queries in the comment box or either on the Telegram group, whose link you can find in the description of this video as well as the about section of the channel. And if you are new to the channel, then I just want you to go through the content of the channel which we are trying to make, and if you find this video to be useful and interesting, then do give us a like, and also do subscribe to the channel for getting the notifications at the earliest, and do press the bell icon. And there's a problem of the day series which is going on, which already have been completed for the last month, whose results we're going to share pretty soon. So try to participate as much as you can, and as I said earlier, if you have any doubts anywhere, feel free to write to me or on the Telegram group, where we have a very good community. So thank you so much for watching. That's all for today. We'll be moving in such a similar video. Thank you so much.